Thank you. Hi, welcome to my talk on iOS security. We will do a deep dive in two parts. And mostly for the last few years, I live and work in London I used to work for various startups, and now I'm in a medtech startup called Epsi. And as an engineer in a customer-facing health related industry, our users' data security is one of my top priorities. And I was talking a lot over the last years about the wacky topics on iOS, from the big O notation to the security to delving into Apple Pay. And today we will try to cover everything we could cover in 2 hours. And my sole goal here is that if you've joined this talk without any prior knowledge of protecting your users' privacy, after these two parts, you should be able to open your app, the app you're working on, identify the potential threats, fix them, and probably design future features with security in mind. So in the first part, we'll cover why one should bother to actually fix the security issues they have. We will think, is there any life without a jailbreak? Because there is this common thinking that if you want to do iOS pen testing, you need a jailbroken device. We will look at the tools we have for both jailbroken pen testing and non-jailbroken pen testing. And we will have a look at the platform overview, which is what do we have to work with and things related to that. And then in the first part, we will cover the very basics of the iOS security engineering, which is owasp, and the data protection layers. And the second part, which happens after the 15 minutes break, is a proper deep dive in the penetration testing in more details, which is significant parts of the system you should be aware of, the APIs you might want to test in the first place, and certain unusual attack vectors, as in, did you ever think to check whether screen time in settings leaks any data about your application? And before we actually start, as you might guess, I have to give this disclaimer, because surely once you hear it, you won't even think about doing something shady, and everything I cover today is purely for education purposes. Please don't break things, be responsible, be ethical, and the single goal of this talk is to raise security awareness. So first things first, why should we bother about caring of mobile security? Because these days people care a lot about desktop securities. There are numerous antivirus programs. There are weekly news about the zero-day exploits, about patches, yada yada, and they don't happen on mobile that often, unless it's a rooted Android phone with I know, updates from the previous decade. So how come we care so much about desktops and we don't really care that much about mobiles? Because we take a mobile phone in our hands and we rarely see an antivirus installed. And do we actually have to install an antivirus on a mobile phone? And why that happens, and who should we thank for that? Well, Apple themselves, in iOS Security Overview, the document they publish with every major iOS version, and the most recent one, as far as I know, is 13.4, which they covered in spring 2020. When it comes to iOS, we all are strong believers that it's secure by design, and Apple says we've built advanced security into our products from the ground up to make them secure by design. What does it mean? It means that this whole Apple ecosystem was designed in the most optimal way to prevent possible attacks, whether it's the malicious user or the attacker trying to exploit some part of the system, or the apps you have, because they build the infrastructure for us. And they want us to build apps in a safe way. And as it's secure by design, whatever we do out of the box should be safe and secure. So the question is, what does it mean for these two-part talk if it's secure by design? And the answer is, well, there is nothing to do here anymore, folks. Let's chat about something else. Apple is secure, the system is secure. Sadly, I would love to finish that talk that way, but it doesn't work that way, especially nowadays. If you remember the headlines like 4 or 5 years ago, every single zero-day exploit, every single jailbreak would cause havoc on the iOS market. Headlines would be full of shock and disbelief. But what does happen nowadays? Nowadays, the price of 0 days for iOS is lower than the price of the same ones for Android. We have so many problems and exploits and various issues security-wise on the iOS platform for the last few years that people are not surprised anymore. And that's why these days it's even more important than ever to focus on protecting users' privacy. And that screenshot, you can see the iOS 0 days pushes the price for Android ones lower is slightly outdated, as in it's like 2019, maybe it's a single one-off thing. Sadly, it's not. If you follow the 0 days changes and the news headlines and the work Google teams do, for example, to cover the exploits on iOS, you might have heard all of that already. The voice over escalation of privilege, the mail app exploit, new jailbreaks, which are happening now almost every month, these iOS exploit chains, you name it. For the last 5 years, we had probably more vulnerabilities and exploits we did have in the past for the 5 years before. And unfortunately, that is a problem, because nowadays the mobile devices are the main source of users' private data. And for us as engineers, testers, managers, and in the end users, it means that while the system itself could be secure by design, as Apple claims, it's still our responsibility to build apps with the worst case scenario in mind. We have to think about what might an attacker get, and we might think what might happen is if the system is actually at fault. And also we should think, what if the system is safe, but something on our side is at fault? And we have to think about the data we store and whether we actually have to store it and whether we could avoid that in the future. And these worst case scenarios, they might happen because while we store lots of data, we rarely protect it well enough. And that's the tricky bit, the caveat here, because before we protect something, we have to know what actually we protect and from what. And when it comes to protecting mobile apps, it's usually believed that we are working on mostly protecting our users from some hacker hacking into their accounts, stealing their own data, and so on. We don't want attackers to do that because we'll be sued, users will be upset, our business will suffer. But that's about a user to attacker direction. There is also another part of that, which is the attacker trying to exploit our app to attack our business or servers or the internal data we have. And the user is not really involved into that because the attacker doesn't target someone personally. They target us as a business. And even though it's pretty terrible if the attacker gets access to the user's personal data or read their messages stored on the device or access their credentials or change their passwords, steal credit cards PIN, this is not the biggest problem we might face, because they might actually access the servers themselves, and usually that happens at the default of front ends, and probably that's why. But to make it safe, to protect themselves, backend analytics testers, no one should ever trust front ends, and it won't hurt if you make a screenshot of that page and just send it to your coworkers just in case they didn't know that yet. Because even when you don't trust the front ends, when you keep the backend or the database as the single source of truth, it still is not enough. There is where the second vector comes in, and that's where an app itself might contain something which can be used by an attacker to cause harm to your business. It might be, let's say, a plain text API key encoded into your app somewhere, which gives access to your app's analytics. So a malicious company can access your analytics as well and send you either fake trace to compromise your data or just subscribe to all your changes and sell them to competitors and damage your business. So it can happen in any way possible within the app. And as far as the backend doesn't check every single thing interacting between the front ends and the backend, something might go wrong. If we rely on some condition in the app code and the backend itself doesn't verify the calls we make, the problem might arise from injecting the different condition into the app and altering the logic which should be hidden. And that's what we will be covering today, the possible places where this interaction is at fault, where an attacker might not target the users, but target us as a business, or might target everyone around. And to set up that flow and to uncover these issues, we have to set up the environment first. And that's where the main question comes in. Do I actually need a jailbreak? And what is the worst case scenario where an attacker has access to our app or to the users using the app? The worst case scenario is when an attacker has physical access to the device with our app installed. Even more terrible example would be an attacker getting access to the source code to just audit it directly, but that's a more rare scenario. So most likely an attacker would have the device jailbroken because that gives you a better visibility over the things going behind these curtains. But as we will see later, it's not really that much mandatory. Jailbroken devices and non-jailbroken devices have their own pros and cons, but we as engineers can choose which one we want to use for our pen testing, and that's where we can look at the pros and cons of them separately. Jailbreak itself is fairly straightforward. You have a phone and you work with what you have. It has a limited toolkit, so you can't do that much, even if you want to. It's fairly hard to install apps from IPAs without resigning and repacking them straight on the non-jailbroken device. However, it allows you to test out the real-world scenarios. You can look at the actual things your users will face, and if an attacker gets a brief access to the user's device, most likely they won't be able to jailbreak it quickly. So that's what you might work with in most cases. That sounds fairly legal as well. So a non-jailbroken device, what could go wrong? And it's always possible, as in you don't have to find a specific version of the iOS installed to test something. You can just pick any device in the store and test the app you want to test. Jailbreak, on the other side, is slightly different. Sometimes it's legal to, for example, jailbreak phones for someone else in exchange of money. Sometimes it might be illegal to use jailbroken phones when you do a contracting work. And don't quote me on that in 10 years. I'm not a lawyer. Here it's better to save than be sorry. But I would strongly recommend you research the laws of the country you're in if you want to, especially if you want to work as a freelancer and offer the contracting service and use the jailbroken device. Jailbreaks are sometimes unstable. That's a stretch. They're mostly unstable, but for the scenarios we might them to use, the reset or reboot is not that much of a problem. So that's something we can work with. But again, I wouldn't suggest jailbreak your main or only phone. And sometimes it's impossible to make a jailbreak because, well, not all versions are that jailbreak prone. However, these days, it's almost like Christmas comes to security engineers like 5 times a year, and the majority of the new versions have some kind of jailbreak you can use for them, especially if it comes to older devices. Also, jailbreak sounds fancy. You can just walk into a room at an interview and say like, well, yeah, I have a few jailbroken devices. I use them for engineering and pen testing, and that's it. I'm kidding here. Don't do that. However, the best benefit of a jailbroken device is the versatile toolkit, because you can use lots of tools, including the ones for easy sideloading, or you can inject something straight into the memory of a running app, something you can't do on a non-jailbroken device. And that is the main difference. If you want to find out what happens inside the app, as in like disable SSL pinning or patch some part of an app, you can do it on a non-jailbroken device. You just way more hassle. You'll have to change the app, repack it, resign it, install it again. It might alter some states. However, with a jailbroken device, you can just connect directly to the memory and read and write into that. However, there are cases when there is no jailbroken device at hand, which is perfectly normal, and that's what we have to work with. Like, you are casually strolling into an Apple store, and you have this urge to pen test someone's app, like pre-installed on an iPhone, and you just grab a phone in an Apple store and you just do your engineering testing. That's where the non-jailbroken device would work. Or sometimes you have to live with that as the specific feature you want to test is on a beta version of iOS, and there is no jailbreak for that version, or there is no jailbroken device for that version. And if you want to test a new just released feature, you might need to do it on a non-jailbroken device as well. And for that, given now the iOS 14 beta might come out pretty soon, hope so, we have to know how to work with non-jailbroken devices as well. So your flow with a non-jailbroken device would start with downloading application package, IPA file. And if you are doing a bug bounty program, if you are working as a security engineer for someone, most likely you'll be provided with an IPA file because in most cases that's a part of the bounty program. However, sometimes you don't have access to that, and that's where there are certain tools which can help you to extract the file from the app, for example. We'll look at them later. But that's so far is the trickiest bit of pen testing on a non-jailbroken device. Once you have that, you will set up the environment, and after you're doing some modifications or embedding some tools you need into this executable file, you'll have to repack it and sign the package so you can sideload it into your mobile phone, because surely you can't use App Store to distribute that. Install the app on device, connect to it in the debug mode, and keep going with the security testing. And that sounds pretty straightforward, but there are certain conditions which might make this process harder, and we will look at that from both perspectives of an attacker, as in, what do I do if the app can't connect in debug mode? What do I do if there is some anti-debugging protection? And we will look at that from the perspective of the security engineer, as in, what do I do if I don't want someone to connect to my app in the debug mode? What do I do if I don't want someone to inject custom dilib into my code? And to do that on a non-jailbroken device, there are certain tools you might want to use for that. For example, the FreePA, which is an automated wrapper script which allows you to unpack, patch, resign, deploy apps, all of that with a non-jailbroken device. It works with the Frida behind the curtains, which is one of the most famous apps for security engineers. We'll cover it in the jailbroken tools section. And it contains kind of like two modules. One is the module used for unpacking and deploying, and the other one is for connecting the patched app without reinstalling. The other app is a funny one. So Apple Configurator the second has a bunch of features. It's a tool from Apple with almost a decade's history. It was or is originally meant for managing multiple devices, as in a company, in a school, but also it gives you an easy access to the device logs, and that's what we can use it for, because if you're guilty of leaving prints with passwords of your code in your code somewhere, that's where they will leak. So you can use Apple Configurator too on a non-jailbroken device to see the logs of the app. And the third one is Objection. It's a runtime exploration toolkit, which was built to help you assess the security posture of your mobile app, which is you can test whether it's secure or not without needing a jailbreak. Supports both iOS and Android, allows you to interact with the container file system, bypasses SSL pinning, dumps keychains. You can do some memory-related tasks. You can dump memory, you can patch memory, and you can even manipulate objects in the heap. So that's a very cool tool. Built in Python, looks fairly fancy. Terminal interface, however, auto-completion, so you don't have to remember all the commands by heart. So that's what we would work with if we have a non-jailbroken device. And that's perfectly enough for the probably 99.9% of the tasks you might want to do. Once it comes to jailbroken devices, though, there are way more features and way more tools. So Frida, which I already mentioned, is the dynamic instrumentation toolkit for developers, for reverse engineers, for security researchers. So it's some kind of a Swiss knife you can use to inspect almost every single part of the app flow you want to inspect. The second one is a passion fruit. It's a simple black box assessment tool, and by simple, it's probably a stretch again, because it has a beautiful UI, it has a web interface. It's very simple to use because you just run passion fruit in command line, you get the localhost spinned up server, and you do whatever you could do in Frida, but in graphic unit interface. So that's very convenient, very handy, very easy to navigate the app or prepare your security research papers. and I can strongly suggest you either use that, try it out, contribute to the community, because passion fruit had been developed for the last few years. It was a great success. And as far as I know, they're aiming to make a new release fairly soon. And the third one is less of a tool, more of a script kind of thing, which is SSL kill switch. Quite often there is this belief that SSL pinning, certificate pinning can protect your app from everything. Well, it can, yes, in some very specific scenarios, but it mostly protects the users, as in your user sits with your app in a Starbucks using public Wi-Fi, and that's actually not a public Wi-Fi, but an attacker doing the man-in-the-middle attack, disguised as a router. And that's where SSL pinning is great for the user. But once an attacker wants to explore the internal logic of our app, once they want to see the actual data we send and requests we make, that's where SSL pinning is possible to bypass. And one way to bypass it is using the SSL kill switch, because it just disables SSL pinning and certificate validation for all the apps on your iPhone. It makes your phone very insecure, as in, don't do it on your main device. But that's really great to actually explore and then test certain routes in your app. And well, as I said, there are way more tools and way more ways to test and explore things. And I honestly trust that you will manage to find the ones which make your life easier if you want, because even the set I gave you is perfectly enough to do your first steps with the security pen testing. And on top of that, there is a bunch of pretty neutral tools used not only within the mobile community, but and not only for pen testing, obviously, as in the Suite community, which is a way to proxy HTTPS traffic, which is very handy if you already did the SSL pinning bypassing, and then you want to actually navigate through all these routes in a more convenient environment, which is very customizable, scriptable, allows you to simplify some of the routines you would do. And another one is the Hopper app, which you probably already know, the Hopper disassembler, which is a reverse engineering tool that lets you disassemble, decompile, debug your applications, not yours only, obviously, also those in bug bounty you participate in. And with Hopper, it's very convenient if you know some part of the logic of the app you want to disable, as in like front-end side, client-side only password check, which you can just nullify and bypass using Hopper, then repack the app, rebuild it again. You can use it for both non-jailbroken and jailbroken devices. And the third one is iMazing. So this is the file manager. It allows you to extract APIs on non-jailbroken devices. And that's pretty convenient. That's not like a 100% working tool, because the way they do it in most cases is they kind of do a backup of your app, and they, after that, try to extract the API from the backup, which is unencrypted. But that might lack some data if some data was stored with the key which disallows storing in the backups. And a side note, if you ever want to save 200 gigabytes of photos to iCloud, and then later you decide to delete them from iCloud and your phone on a non-jailbroken device, including the previews, iMazing is probably the only, but at least the fastest way around, because you can just navigate to the DCIM folder, you can remove it completely locally, and you can remove the database with the stored references. So that's a very convenient tool. And yeah, that's it. That's the toolkit you might need to just start doing pen testing, and then later you can start writing your own modules for, let's say, objection, or contribute to the open source, or explore the tools further. And if you do use these tools, and you do not use a separate device for pen testing, backups are utterly important. As in, the backups is the way to explore the hidden nuances of the platform, and that's where comes the actual platform overview and what is hidden inside that platform. So iOS is based on Darwin, and it has a secure boot, it has hardware-backed keychain, file system encryption, it has the update rollouts, which is a nice benefit comparing to Android, which means we pretty much can drop support of iOS versions and support only the most recent 2 versions. And we get the security updates almost in a mandatory fashion straight away. So in general, our users are more secure, and our developers within the iOS community are less nervous because they don't have to support something from like 5 years ago. Again, in most cases, especially if you work for recent companies. And iOS apps are isolated with Apple's iOS sandbox, which used to be called seatbelt. And that's the mandatory access control mechanism, which describes what app can do and cannot do, can access, cannot access. And I won't be covering the first bits because that's probably what we hear almost every dub. But if you want to properly delve into that, there is an iOS security overview, which is around 100 pages of architecture and descriptions and technical details. And it has beautiful links to patents as well. That's hidden in support.apple.com, but they have all these certifications and security tests made for every single bit of the system. It's not indexed, but if you use the iOS security overview, you can just find these hilarious or sometimes very interesting certification bits on the details of the iOS architecture. But for now, let's focus on the seatbelt. So the sandbox itself is definitely not new. It was first introduced in OS X 10.5, Leopard, and it was almost 13 years ago. So back then it was called seatbelt. And the idea of that was very simple, right? Hence it's called seatbelt. You can just fasten your seatbelt just to be safe on a car journey, but that's your choice. They ask you to do that, they fine you if you don't do that, but that's your choice because you want to be safe in that car. And same comes with developers. Developers should voluntarily enforce the sandbox upon their applications to restrict their access to the system. It's not mandatory. It wasn't mandatory, obviously. And that's why, as you can probably imagine, not many developers did that. And because of that, Apple couldn't do much because the seatbelt was voluntarily enforced to people. So what happened after that? The rest is history. 4 years after that, in 2011, Apple introduced an entitlement which gives the app the sandbox, and that entitlement would be added automatically once you're signed for App Store distribution. So because of that, there wasn't that much you could have done on OS X. And on iOS, it was implemented in a very similar fashion by restricting apps to the separate containers. So Apple learned their mistakes and they stopped doing that voluntarily. They made it mandatory, and that's what we work with nowadays. And even though we have the sandbox, which you can see is just a container, right? Given the sandbox, we might be pretty sure that apps would rarely interact with each other, unless some huge company would introduce a way for them to interact, like deep links, app groups, shared folders. But which company would do that? Like, why would you do that if you already made a safe system? Well, glad you asked, because that's what we work with. And there are lots of things on iOS system which are not really safe. And that's what we are looking for, as in usernames, passwords, location data, facial data, the advertising data, address book entries, payment information, and lots of other things around the system which can be either lying saved in some documents folder, or in this sandbox container, or in user defaults, in the keychain, anywhere. And that's what an attacker would look for, and that's what we should protect in the first place, or ideally just never store. And thanks to the community, almost 20 years ago, in 2001, the OWASP, the Open Web Application Security Project, was created. It was initially focused on web applications, as you might guess from the name, but these days their focus is on improving the security of software. And that is the kind of like the main book you would probably start reading if you want to understand the common cases of security between different software projects and dive into the specifics of mobile or the specific of iOS. And the essential parts of that separate document on mobile security in general and iOS security in particular, which I strongly recommend you to follow on the GitHub repo, because they constantly update it and you can see the up-to-date changes to what matters most in the security world nowadays. These main parts include the device bit, which is the local storage, the interaction with the platform. They include the various APIs, as in communication with trusted endpoints, for example, which is where most of the data is leaking out, or the authentication authorization locally on the phone, or the prevention of these things like the anti-reversing mechanics to prevent stuff. And if you follow closely the whole direction, the whole idea of the OWASP guide, you can see that the main concept is that as little sensitive data as possible should be saved in permanent local storage. And if you do save something there, you have to protect it as much as possible. So how do we protect or interact with local storage? Luckily, we have the data protection APIs, which give us fine-grained access control to this flash memory. These APIs were built on top of the Secure Enclave processor, the SEP, which was first introduced with the iPhone 5S. And since then, the SEP is a coprocessor, which provides you various cryptographic operations to protect data, to manage the keys. And even if the operation system's kernel is compromised, the SEP itself has a device-specific key embedded into that, into its hardware, and that ensures the integrity of that protection. So even if the kernel is compromised, the SEP is all right. And that's kind of how it's set. We have the hardware key, it interacts with the file system key, we have the passcode key, it independently interacts with the class key as well as the hardware key. And all of that boils down to file metadata signed with the file key, and it goes to the file contents. So that data protection architecture is, as you can see, based on this hierarchy of keys, right? And the different IDs, the user passcode, which is derived from the user passphrase, they sit at the top of that hierarchy. And only together they can log the next level, the so-called class keys, which are kind of connected with different app states, like device logged, device unlocked. And every single file stored in the iOS file system is encrypted with its own profile key, which is, well, good news, but it's contained in the file metadata, which is encrypted with the file system key. And if you get access to that part, you can de-encrypt the file, but we'll get to that later. So the data storage in iOS is organized fairly straightforward, the hierarchy of keys, files, metadata, and to interact with that, we have access to so-called protection classes. So the first and most common is the complete protection, which means passcode, device UID, write from the memory shortly after the device is locked, the complete protection. There is also the protected unless open kind of protection, which means by default the file is protected, but once it's opened, when the phone is unlocked, the app can continue to access the file even if the user logs the device again. And you might think, like, why would you introduce such a thing if it's not that different from the first one, but less safe? Well, there are a few examples when you might want to unlock something, but you want to keep the app's access to that file. As in, imagine you send an email and you have an attachment, and you want to download that attachment in your mail app, and your email is secured and encrypted, but the downloading attachment in background is still happening, so you want to keep the access to this downloading file in background, even if it's encrypted. And that's where the protected unless encrypted unless open comes in. The next one, and the default one, is protected until first user authentication, which you can guess is unlocks the device for the first time after booting. And well, since then the app can always access the file. And that is fairly dangerous because you might just turn on the protection class out of the box, and that's what would happen, right? The attacker might see that the app already is closed, but the file is still unencrypted and will be unencrypted until the next reboot, which is a rare thing on iOS devices. Last, and probably least, is no protection. The key for this protection class is protected with the UID only, so it's stored in the region of the flash memory of the iOS device. And the only purpose of using that part of the memory is if you need something to fastly wipe remotely, for example. So that's something you would use rarely. And then there is the keychain, right? The single keychain is available to all apps across the whole platform. And the access to these keys in the keychain is controlled by the security attributes access group. Keychain was meant to store short, sensitive bits of data, and bits is the accent. So it's either encryption keys, session tokens. This whole keychain thing is an SQL database, so you can, if you manage to de-encrypt it, which is not a hard thing to do, you will be able to read it as an SQL database with any SQL reader. And you can share the keychain between apps signed by the same developer using the access groups feature. And the only exception here is if you transfer the app from one account to another one, and on the new account, even if you keep the bundle ID, and even if you use the actual identifiers, it's pretty hard to do. So you'll have to migrate the data properly beforehand. And there are numerous keys, as you can guess. The keys are fairly straightforward, as in the accessible always means that the file in the keychain is always accessed by the system, whether it's locked or unlocked. The next one, accessible always, this device only, is the same as the first one, always accessible, locked, unlocked, but it won't get into the iCloud or iTunes backup, which means, as I mentioned in the past, if you do a backup hoping that you can find something secret in the apps folder, this key will prevent the data from leaking into backups. The third one is accessible after the first unlock, which means once you restart the phone, you have to unlock it first for that file to become accessible, but once you unlocked it, it will be accessible till the next restart. The fourth one is a twist in that. Accessible after the first unlock, this device only. So as you can guess, same as the previous, but won't be migrated to a new device or to the backup or to the iCloud. The next key, accessible when unlocked, means what it means. It doesn't matter whether you restarted or not restarted, the file is accessible only when the device is unlocked. The next one builds on top of that, only unlocked, but doesn't get to the backups. And the last one, accessible when passcode set, this device only means unlocked only, no backup, and you need the passcode set, which is the best and most secure way to control that. And also we have the keychain access control flags. So the ways to define the mechanisms which users can use to authenticate the key, as in the device passcode, or we can enforce touch or face ID and no validation, or we can do touch or face ID and invalidate the token at some point, or we can do touch and face ID and we also need the passcode. So these two keys, the second and the third one, they are protected by the secure enclave. So the keychain itself doesn't store the actual value, it stores the token to access the actual key in the secure enclave, which means it's fairly good. And in case you want to use these mechanisms, it's better to test first whether the passcode has been set, because otherwise it won't work, right? And that actually is supported by the majority of new versions. So from iOS 9 onward, you can check whether a lock screen is set or not using the LA context. So you can set up the check for the enabling the passcode, and then you can see whether that check has been ran, and you can remove the keychain if this is a new device, because when the user logs out, we want to wipe out the keychain, but we also want to wipe out the keychain when the user installs the app for the first time ever, because if you do the reset and you sell your device to someone else, the keychain stays, right? So that's a very rare but still possible attack route where you buy someone's device and you install an app which relies on the keychain, and if the user had that app installed, the keychain will keep their tokens. So make sure you reset the keychain as I'm showing here on the first launch as well, because that prevents the very private and very safe data from the keychain to be leaked to the new user. So what could go wrong here? First thing first, make sure nothing sensitive like passwords, keys, tokens, anything, any personal data of the users is stored in user defaults, or if you see in your code NS data, write to file, file manager, all these things are triggers, which mean that you might be writing something and you probably shouldn't do that. If you do a pen testing of a new app, search for these words, search for the user defaults, search for the NS data, writing to files, writing to file managers, check for the core data and databases because they might not have encryption, which is almost the same as just storing a file on the drive. And if the encryption is used, make sure that the secret key is stored in the keychain with the secure setting, ideally enforcing the passcode, ideally without backup support. Because what's the point in encrypting your database if you store the key in user defaults? That's what happens, and you might be laughing, but that's what happens quite often. Don't do that, please. If you use something else, like let's say a Firebase, be careful with the Firebase. I look at that issue every year and it never goes away. Google claims it's by design, like security by design. But even then, more and more developers are migrating to Firebase. It's sometimes the only way to get remote configs. It's a quick way to hack around the database. It's an easy way to set up A/B testing. You might want to keep your Crashlytics, Fabric after their migration. So if you do migrate to Firebase, or if you do use Firebase, keep in mind that they have these feature by design where you can take the project ID from the info list and you can just put the /.json in the end of the root, and boom, you see the whole database public as a JSON file. That can be disabled in the security settings. They don't enforce it as a setting by default for some of the flows, but please look for that either using the Firebase scanner on GitHub or just by checking that the Firebase settings are as secure as possible, especially if your team is big, because there are quite a few toggles in there and some of them are not really secure the way they could have been secure. If you use Realm, and Realm by no means are supplied by Apple, but they're still worth noting because they're very popular. By default, Realm is unencrypted, and unless there is the configuration for encryption enabled, it's like a plain text almost. So to do that, you have to generate the encryption key first, and after that, this is a very, very straightforward process. As in, you just provide the encryption key to the Realm configuration, and you use it the way you would always use it. And the funny thing, if it fails, if the encryption key is wrong, the one you provided, it will fail not as in like the key is wrong, it will fail as an invalid database error, as another way to kind of misguide an attacker, which is a really nice touch. So that's a very quick way to protect your Realm databases. And on top of that, if you want to do the kind of like non-jailbroken device dynamic analysis, the iMazing tool I mentioned earlier has a few ways to do that. So as I mentioned, they use a backup, like they extract the data from the backups. At least that's how it seems it works. And if you use the keys smartly, not all the data will get into the backup. But if you want to test whether that happens, if you want to test the quality of your backups, for example, you can trigger the functionality that stores these potential sensitive data, connect to the iOS device, launch iMazing, search for the app, extract the app, rename that file they're extracting into a zip folder because it's a zip file, and then you can use objection separately from that if you want to dump the keychain items from a non-jailbroken device, because keychain is still accessible and you can still de-encrypt it. So the silver bullet doesn't exist here, but if you want to make it safer, avoid storing anything on the device and please focus on the user security here. There are other locations for the storage of the sensitive data which do not just come to our mind straight away. For example, you might see that some people are adding the autocorrection type no and security text entry true to the password fields, which is quite important because that's one of my favorite locations for your data. For example, the data here will get into the keyboard cache, and that's the thing where you type something, you get the autocorrection, you get the autocompletion, and it stores up to 600 words in there, so you can access them in library, keyboard, dynamic text folder, and that's in hex data, but you can unencrypt it. And what you can do, you can find for, let's say, search for emails in there, and probably something after an email might be a password if the autocorrection type no is not set. There are also logs. We all love prints. Please don't do prints on the release builds. Don't do them on the debug builds either. Disable that when you ship your app. Backups, as I mentioned, is a nice place to search for. And also the overlays, like when you switch in the mission control between your apps, you can see these like sometimes blurred in some apps screenshots. So blurring is a good thing, because otherwise these screenshots are stored in the cache, and an attacker might get access to that cache and see the protected parts of your app. And also the memory. So dumping the memory is a trickier part, and that's where we will get to in the second part of the topic. So with that in mind, as owasp quotes beautifully, the true excellence at mobile application security requires very deep understanding of mobile operating systems, but not only, it's also coding, network security, cryptography, and a whole lot of other things. And I encourage you to look into these things, because otherwise you might have a wrong feeling of security being something preventing the users from getting the best experience, and feeling that in a perfect world, no one would be able to use anything. They would be just super secure. But is it a security if people can't do anything with your app? Thank you very much for your attention. I'll see you in 15 minutes at the second part, where we'll get to the actual pen testing bits and weird vector attacks. Yeah, welcome back. I honestly feel like a deja vu looking at these slides, but for those who just tuned in and missed the first part, my name is Vadim Drobinin. I live and work in London for a medtech startup Epsi, and we care a lot about our users' private data and security. And I'll be sharing the second part of my main takeaways from ranting about security for the last few years. In the first part, we covered quite a few things. So hopefully by now you already know why we should bother about security, and what do I do if I don't have a non-jailbroken device, and what tools would I use to do the actual pen testing, and how come there is a sandbox, and what is often so wrong with the mobile security in general and iOS security in particular. Let's do a deep dive now. In this part, we will look into more kind of fine-grained parts of the APIs we work with and the security problems we face, as in the local authentication and network APIs and the interaction between apps, the web views, which is a huge topic and still is a case for mainly vulnerabilities in our apps. And as well, we'll explore some unusual attack vectors and learn how to fight with the jailbreak detection and how to protect from those fighting with it. And then we'll get some further directions if you want to learn more or see the actual guides on how to do it in the first place. So the main bit I would like to cover here in local authentication on iOS is the actual interaction with the app and the user using the credentials stored locally on the device. The local authentication consists of two parts. The first part is the local authentication framework, which is a high-level API used to authenticate the user via Touch ID, Face ID, and the app can't access any data associated with the enroll fingerprint, and it's only notified if the authentication was successful. So it's a black box of some kind. We know whether it was successful or not, but we don't know the specifics. And there is also a security.framework, which is a low-level API for keychain services. It's a secure option if your app needs to protect some secret data using these biometric authentication, as in the Touch ID or the Face ID. And it gives the access control on the system level, so that's harder to bypass. This framework has a C API. There are a few open source wrappers of some kind available if you don't want to write C code. I can't blame you for that. And that basically makes access to them as simple as to user defaults. The security framework lies under the local authentication framework, and Apple actually recommends to always default to higher level APIs whenever it's possible. But if you want this fine-grained access, you might consider security framework as well. And that actually sounds really good. I mean, at least that is secure, right? Right? I mean, it sounds pretty much secure, but as you could have already guessed, probably from my rantings, it's not at all. If you look at the actual way it's set up, you can see that there are multiple parts of our authentication interaction: the user space, the operating system, the secure enclave. And well, the secure enclave bit is fairly secure, as it says. It has Touch ID, it has credential management, the key management, and they are nicely wrapped and interact with the user space through the operating system using the local authentication and the keychain. And the user space itself has the application we want to protect and the security framework underlying there with the security items APIs. So the secure enclave, as I said, is pretty much secured, but as it's only on the right and your app interacts not with that directly, the most vectors of attack would target not the secure enclave, but actually injecting the malicious code into your app's IPA to compromise the interaction with the authentication. Imagine the scenario where, let's say, you check whether something is authenticated to show the next screen. As far as this next screen doesn't rely on the data containing in the secure enclave, you can just disable this check. And after that, access the screen hidden away as it's not secure at all. And that's where the security enclave's integrity, it doesn't matter that much, because if you want to use it to its full extent, it should be used to access things stored right in the secure enclave as well, which you should keep in mind, because otherwise you might rely on the biometric authentication, but you might miss these very, very important bits stored inside the data. If you look at the actual interaction with the local authentication frameworks, you can see that there are multiple stages you can bypass, whether it's device owner authentication, which requires the Touch ID and passcode and fails if it's not set, or the device owner authentication with biometrics, which relies only on the biometrics. And to my knowledge, unlike macOS or Android, iOS doesn't support these kind of like temporariness of an entry's accessibility in the keychain. If there is no additional security check when you're entering the keychain, then once the device is unlocked, the key will be always accessible. So that's an example. We've seen a very similar usage of the LA context in the first part of the talk. That's an example of how to evaluate whether the user is available to go further. If you want to see how to bypass it from the attacker's perspective, so you can learn how to protect better, I strongly recommend you this talk called Don't Touch Me That Way, which walks you through all the stages of bypassing the local authentication. Now that we pretty much understand what's going on with local authentication, what about the network interactions? And there is this app transport security introduced by Apple, the fancy name for a very common set of rules, which covers the URL connection, URL session, the URLs, which forces the public host names, so not AP addresses, not unqualified domain names, no TLDs of .local. It prohibits HTTP connections unless you specify them directly, and that's something you should approach very, very cautiously. And it enforces the transport layer security as well, locking its version. There are a few more requirements to keys exchange, which is something you won't be interacting often that much, but that's what you would be looking for. And these are the things predefined in the system. However, we have to protect this interaction anyway. And in the first part, I mentioned that the SSL pinning is not 100% secure. Since my first part, nothing really changed. It's still not as secure as it could have been. And that's where, in the worst case scenario, as I mentioned, the user sitting in a Starbucks and using the public Wi-Fi and sending something private over the network will be certainly to some extent safe because you have the certificate pinning, but it won't protect the app from the attacker themselves to bypass this pinning on their own device. And that's the main takeaway. Like, if you want to protect the network authentication, you should care. The first thing you should care about is the app transport security, which should be configured according to the best practices by Apple. And if you want to deactivate certain bits of that, do it only under very specific circumstances when you are 100% sure that that's what you need to do. Even though everything I said about the SSL pinning kind of makes it sound like it's not needed, it is needed. Don't take me wrong. It's a great way to protect your user from the man-in-the-middle attack, and there are lots of scenarios where you want to have it in place. If you do that, please don't hardcode the passwords or keys in the app, because that kind of kills all the efforts. And if you're, let's say, building your own browser the hard way, not just opening the URLs with the Safari view controller, and you have like numerous web views, you might want to disable ATS, because you might want the user to use your browser to access the websites without HTTPS connection, for example. And another scenario would be you have a specific domain under your control, so you can disable ATS for that domain only. And if you want to open the third-party websites and web views, you can allow arbitrary loading of this web content for that web view or for these web views without affecting the overall app's interaction. Please keep in mind that it's not the most safest option you can choose. And if you have multiple domains under your control, you can ask them to ask the system to acknowledge that and allow you to interact with them without supporting, let's say, the TLS version of specific kind. And that's a simple example how it would look, the bypassing of this protection. It's pretty customizable. Sometimes if you do that, it's fairly hard to explain to the App Store review team, but to me as a user, that's a great thing. I know that developers will have to go through some additional effort to actually do that. And that's something you might use if you do the patching and security analysis of some apps, because you can replace this list and disable something arbitrary to see if you can get some more data you're looking for. Now we know how to authenticate, we know how to interact with the server, and it leaves us with local interactions, whether it's the system, with the user. And as you know, the majority of the apps we build and we ship and we install, they're running under non-privileged mobile user. So it's not a root user with all the privileges to access all the hidden parts of the system. It's a mobile user. And each app has its own unique home directory. It has sandbox around it, the container we've seen in the first part. And to access some protected resources, some protected data, we have to address some capabilities. We have to ask for special permissions, so-called entitlements. And if you're watching the field, if you're watching the space, there was a 0-day recently in parsing one of these entitlements. It got fixed in one of the iOS 13.5 versions. And this whole exploit, which was exploiting the wrong parsing of the XML, it actually fit in a tweet. Like, imagine you can bypass the sandbox with a tweet. How beautiful is that? Please don't misuse the entitlements. It's a very powerful tool. And permissions themselves are a funny thing. They are so easy to abuse, so easy to misuse. Please never ask for more permissions than you actually need at that very moment. If you don't need access to the photo library on launch, if you don't need access to the health kit straight away after the user downloads the app, don't do that. Because every single permission you ask for is something we really should appreciate, because users put their trust in us. They give us access to their whole library of photos, not to a single photo. They give us access to their location for the time we are using the app, not for a specific one-time location check. And that's where every single permission, if misused, breaks a huge chunk of the user's trust, which we want to avoid by all means. And what is wrong with asking for permissions in general? There is a great blog post by Felix Krause who summarized a very nice list, and that's just a small part of that list. So imagine you ask for the camera access. The camera can record users at any time the app is in the foreground, which is fairly tricky. I mean, we don't have the the flashing thing on our iPhones. We don't know if the camera is filming us when we open, let's say, Instagram. And there were certain things disguised as bugs, but we never know if it's an actual bug where you can spot the, let's say, Facebook app filming you even if you don't open the stories page. So the camera access permission is very powerful. It can run real-time face recognition, so it can detect facial features, it can detect expressions, it can understand what you think or feeling at the moment, just because someone gave you a camera access to send a picture to their friends. And that is fairly dangerous. And it can upload the pictures and videos it takes immediately. So that's where the testing of the roots comes in. We should see that the app doesn't upload something we don't expect to upload. Or we might see that actually that app uploads something, let's say a photo or a video the user didn't want to upload, but we as attackers can get something out of that. And if there is no SSL pinning, we can spot the user sitting in a cafe and see what is their facial expression, for example. And same comes with the photos access. When you give someone access to photos, it gives access to all photos, right? So we can analyze all the photos, we can get their EXIF data, we can track all users' movements based on their photos meta. We can see the location of each photo and map it to the map and see how the user behaves in certain parts of the day, in certain times. We can track all their devices because they might have the iCloud sync, we might have photos synchronized with other devices. And we can use facial recognition to find out who is their social bubble, who they are hanging out with, for example, to target that later. And on top of that, we can surely run way more different on-device recognitions or analysis. We can use the core ML to learn something about the user. And if we store that improperly, or if we don't tell the user what we are doing, this is a potential security breach, because an attacker can find out that we store something which we shouldn't store, or we should encrypt better and get access to that. And if you want to test these in your apps, first thing you can do is to see whether you, for example, cache or store some items you snap from the user, or if you analyze their directory and make some kind of like findings and store them somewhere. So that's something we should really care about. What else could go wrong here? If your app uses the third parties, whether it's via the, I don't know, the Swift package manager, CocoaPods, Cartage, most of them can be actually attacked by the man-in-the-middle attack. So the attacker, given you're on the public Wi-Fi, can supply you with the fake framework, which looks like, let's say, a Llama but actually disables SSL pinning. And if you are working from, I know, some co-working place and making an app build and sending it to the App Store, it might have an attacked version of the third-party framework, which is, well, pretty bad. We can fake the iCloud password alerts by doing the said man-in-the-middle attack, because the iCloud password alert looks exactly the same as the system alert, and the users might be tricked into thinking that this is iCloud. Or we can inject something into web views if the app doesn't use Safari view controller, and that is a huge problem, because once the user types something in a web view, you can store their passwords, you can disable the secure text fields in web, you can gather that data, you can log it, you can send it somewhere else. And we can use the share extensions, because share extensions have huge control over the apps we use them for. You can follow the link in the attachment, the elevation of privilege hack, which was my example for Swift 3, where you could inject the additional windows in the view controller. And same applies to just screenshot typing passwords, because when you type a password, there is this brief moment where you actually see the character and then it gets hidden behind the asterisks. So you can use that to make the screenshot every second, every half of the second, and then knowing where the text field is located, do the simple OCR to recognize the characters typed and save users' passwords. So there are lots of things which might go wrong if you rely on the third-party frameworks, or if you copy and paste codes from somewhere, and you should be careful about that. And that's what you should look for if you do a pen testing of some app, because you have to see whether it has any potential vectors of attack available to the others. Because if you can see that the, let's say, third-party framework versions are not locked, if tomorrow the huge framework you rely on goes under control of some attacker and they change the version, even your CI system might pull the new version and install it on your new build, which will get to App Store, and all your users will be losing data. So please be careful about that. Please see whether you do your own due diligence and you lock in the versions of frameworks. You don't use the public Wi-Fi for something that's security savvy, and you do not allow to interact with something you don't own, as in like the share extension, for example. Which brings us to the inter-process communication, as in the communication between different apps, user and an app, the app and the system, and so on. For example, the most common way is the universal links, which we all know, most of us use. The UI pasteboard, the set of pasteboards we can access from our app and the other apps can access. The custom URL schemes, which are partly kind of universal links, and we will cover that a bit later, but they are still pretty much different. So universal links are very common. They are different from the custom URL schemes in the sense that a universal link looks like a universal normal HTTPS scheme link, and the custom URL schemes look like something : / which is the registered by them scheme, as in my example with Telegram. So the good thing about universal links, the latter, is the uniqueness. It's a way to prevent URL scheme hijacking attacks, because if you registered the, let's say, Facebook scheme, made your own app, got it installed onto the user phone, you might trick the other apps that this is the Facebook, or even the user. It's secure until your website is hacked. So as far as you have control over your website, this is the delegatory responsibility. The universal link is safe as far as you have control over your website. They are pretty flexible, and that means whether the person has the app installed or they don't have the app installed, the app will still be able to resolve this link. In one case via the app, and in the other case to open the browser, the Safari. So that is very convenient, which makes them very simple, right? The one URL works for both the website and the app. You can use them here and there. And they're private. So other apps can communicate with our app without needing to know whether it was installed or not. We can't call a scheme for an app which is not installed, but we can also always try to open the URL even if the app is not installed, because in that case we'll fall back to opening the URL in the browser, and we can prompt them to install the app after that. So I strongly encourage you to use the universal links. But anyway, even if you do use them, there are certain things you still have to test. And first thing is the associated domains entitlement. This is the file within your app where you provide the domains you want to support. Never put more domains than you actually need. Never put someone else's domains, because you don't have access to them and you can't control them properly. And always make sure the domains you control right now actually belong to you, so no one can steal them. Then you can retrieve the Apple App Site Association file. These files have the same common name. They always lie on the domain which is supported, either in the root folder or in .wellknown folder. So you can test that on almost any website where the universal links are supported. You can go to apple.com, you can go to telegram.org, and you will see these Apple App Site Association file. And that file gives you lots of clues. It shows you what kind of the deep links are supported, the universal links. You might see that they have like an asterisk here, which means they support everything. So you can try to bypass some malicious data to the app, which it will try to resolve somehow, and maybe execute your code. Or you might see that there is some very limited number of links supported, like 2 or 3 words, and whatever you do, you can't pass anything else. So you'll have to test only those ones, which gives you, it's a very nice way to start your exploration around the universal links security issues. And then if you have access to the code, or if you have access to debugger, you can look at the link receiver method. You can see how the app actually interacts with the data received. And then you can see how the data is handled, because once we parse the link, we might unwrap some data or fetch something. And then you can see if the app is calling other apps universal links, because that might be another vector of attack. You might be able to use one app which is trusted to bypass some data to another app. You might accidentally force the user to transfer some money to another account by sending them a link, if the app handles that scenario. And that's what comes from this Apple documentation. They say that do not allow universal links to directly delete content or access sensitive information about the user. Why? Because user clicking on a link sees just a web URL, a website link. They don't expect that this link will bring them to the app and remove all their data, sign them out, transfer their money, or send an email with all their passwords. And that's might be a problem if your app relies on the deep links to kind of support some dynamic changes, as in you can provide some universal link containing some words which will trigger some complicated or complex flows. Please look out for them and make sure that the attacker can't access the universal links in a way which might affect the user or the app's metadata. The password is another way to interact between the user and an app, or one app and another app. And this feature in the app can be disabled if the developer chooses to do so. And we can also set an expiration time and date for copied data. But it's our responsibility as developers. Users cannot grant or deny permissions for apps to read their pasteboards. So if you build a password-safe manager and the user copies the password and then they open some third-party app, their password might be copied into that app and sent to an attacker. And that's where this is our responsibility as developers, to set the expiration time on the data copied from our app, or disable it completely if we don't want to make it accessible. So please bear that in mind. And if you build apps relying on some sensitive data being copied, consider setting either the expiration time or notify the user that it's not really secure because the data is sensitive. Apple warns about the pasteboards, which might be named persistently. If you build your own pasteboard within the app, Apple discourages their reuse. So you might want to have shared containers between apps if you want to be able to pass the data from one app to another one. And the universal clipboard is enabled by default, so you can transfer the data between devices. And that is another problem if your password is leaking to someone else's device, if you copied it from your app. And the custom URL schemes are different. So Apple used to say directly in their documentation that if more than one third-party app registers to handle the same URL scheme, let's say Facebook, there is currently no process for determining which app will be given that scheme. Now it's removed from the documentation, but they still suggest to kind of like protect themselves and ourselves a bit more, to specify a reverse DNS string that incorporates your company's name and domain. So it might be like com.example.appname. And that way, as you control the domain, you can at least claim that this is actually your scheme and you own it. It's a best practice. However, it doesn't actually prevent other apps from registering the same scheme and handling the associated links. So the problem is still there. If you have a custom URL scheme, there is no way to define that it's actually yours. And an attacker can trick the user into thinking that their app is the one which should handle the link. If you work with the URL schemes, you can use scan open URL to find whether the schema exists, and that is pretty convenient. So if the schema is not declared, it will return false, which means you have to specify which schemes you expect to interact with. And OpenURL will still try to open it even if the application query scheme is set. And also, if you want to look at the things people are getting creative with, there is this constantly updating list of URL scheme names. So that's something attackers actually look for, and that's something you should protect yourself against, to make sure that if you use the schema, it shouldn't be that known and famous. And again, it's better to use the website or to stick with the reverse DNS string. Which brings us to web views. So web views as a way to move away the user's attention from the app is a very powerful tool. And in the past, we would use the UI web views, which are deprecated. And luckily so, because it was impossible to turn off JavaScript there, which is another attacking route. If your app trusts the contents of the web view and there is the JavaScript which might spy on the user or attack something, this is the place to look for. As far as I know, there is still no way to turn off the JavaScript in Safari View controller, and it introduces the common keychain access, so you don't have to provide your passwords again and again. And there is also the WK web view, which actually has the JavaScript enabled false, and you can secure content as well, which is a nice addition. And it has less issues with the out-of-process rendering, so it's harder to catch any memory corruption bugs in there, which means if you stick to that, it's slightly better. And if you want to play with the web views, you should always look for the following problems. First one is the native methods you can use. They might be exposed for the web view, so the web view might try to access your user sign-out method. Custom web views, they might store passwords, and that means essentially that the passwords might be stolen from them, as well as sessions, keys, cookies, etc. The autofill data is available for the Safari View controller only, which is a good thing. So at least these fields won't be stolen. There is this open source tool, I attached a screenshot on the right, called Where is my browser? This is an intentionally insecure app for training. If you search for some way to implement something on GitHub and you see the Where is my browser repo, don't use this code you see there in your production-ready products. It's meant for the training of the testing engineers. It's a nice way to see the potential problems with the web views. So give it a try. Which brings us to the ways we can actually explore and protect the defenses bit of the iOS system, the anti-reversing techniques. The most common anti-reversing technique is to just shut the app the moment you see that it's jailbroken. Or we can bind to the device to make sure it's not running on some simulator, it's not touched by a debugger. Or we can prevent the debugging by doing some anti-debugging checks. And jailbreak detection is fairly ongoing competition because there is no silver bullet. And once there is some public solution, it gets patched by the attackers fairly quickly or by the other engineers fairly quickly because it's just a nice quest. Like you see how someone managed to fix something and you are thinking about the way to bypass that fix. So that's why you should be creative. You should think a lot about the ways you can do that. And these are just the ideas. There is no silver bullet, as I said. Think about the file-based checks. Think about the file permission checks, as in, if the user can access some file they shouldn't be able to access, it might be a jailbreak. Think about the protocols like Cydia, the market for jailbroken devices, has its own schema, and if you can call that schema, maybe there is a jailbreak in place. You can try to call system APIs, but the problem with all these methods is that as an attacker, I can still bypass it, right? If I see that the system tries to call system API, and if it's possible, it shuts down, I can mock it, and I can prevent the app from calling the system APIs by returning the error or no access error. And that's where, whenever we come up with something unusual, you have to test it properly, but then you have to think, is it something relying on your app? Is it something an attacker might still see in the code or in the memory and patch it somehow? And if the answer is yes, you shouldn't rely on the jailbreak detection. But the other side of the jailbreak detection, even the one which can be bypassed, is the user protection. Because imagine there is a user with a jailbroken device, and they open their banking app, and before that they installed some tweak which actually steals their passwords. We as developers want to protect the user from using the app which might actually steal their passwords, but we can't remove the tweak. We can close our app so the user can't at least type their password in. And that's our responsibility as developers. When you think about the jailbreak detection, even if it doesn't work for attackers, it still works for users. So if your app works with some sensitive data and you think that a user not on a jailbroken device might have some malicious code running in background, so they're not safe, please protect them from that problem. Please don't let them use the app. Send a report, notify them that their app is compromised. or their device is compromised and resolve that one by one. Device binding is simpler. You cannot rely on the MAC addresses and unsafe bindings and the device ID, but you can use the identifier for vendor to do device binding. You can rely on the keychain by locking it to that device only. Or if you use Google services, they have the instance ID, which works in a similar way to the identifier for vendor, so can be used in the same way. The anti-debugging checks are trickier because, well, there is the common way from the, again, developerapple.com. There is the key you can set in ptrace called deny attach, which allows a process that is not currently traced to deny future traces by its parent. And all the other arguments are ignored. So in theory, no one can attach to your app once in your release build you have pt deny attach. And that was pretty nice, but sadly, it doesn't work always, and sometimes it doesn't work partly. And I attached a link here where you can see the walkthrough, the step-by-step explanation of how to bypass that bit. And that makes the attacker's life slightly harder, but now there are lots of automated tools which can actually do that to disable it automatically. And yet we can still make it a bit more complicated. And I'm pretty sure you can go creative with that and make it even more complicated. But this way is particularly funny. It might not work with very dedicated attackers, but it still is fairly good, so I decided to share it with you. So how can we fix that? We can, instead of using just a key, do it in assembly, because sadly not that much people read assembly nowadays. And then we can obfuscate it to make it even harder. So it is still possible to bypass, obviously, but an attacker who wants to bypass it would have to have access to the Mako binary, which is decrypted, and then they would have to override the implementation of the function, and then they most likely will have to swap all our assembly instructions with, let's say, an OP command to do nothing. But that's also harder because you will see more gibberish in your code. And to do that right now in the Swift 5.1 project, you just create a new C file. You call it, let's say, anti-debug C. You create some function with some weird, unreadable name, like a hex representation of the word mdevcamp, with an attached M in the first place. And you invoke from this C code the assembly code. So there is no need to encode these strings because they will be directly compiled. They won't be present in your data segment of the binary, so that's all right. Here we set this pt deny attach command, number 31, to the first address. After that, we clear the next free, R1, R2, and the free. And then we set the instruction pointer to syscall 26. And we use the formerly SWI, nowadays SVC command to generate supervisor call. And these kind of calls are pretty powerful. They usually used to request some privileged operations, access to system resources from an operating system, and so on. And after that, we need a header. Obviously, it's the defaultly generated header. We call our method here, and we force it to be always in line because we don't want it to leak into our data fields. The always in line is not a requirement. It's kind of like we just ask the system to do that, so it might not happen, and that's why we use this weird name of the function. If you want to be even fancier, you can name this function in some very, very normal and usual way, like, I don't know, print user something, and that will be even harder to find because it will look normal. And then you have to include the header into your breach header, and you have to create one if you don't have one. So as you can see, it's fairly straightforward, and that code here is really simple, but a bit more powerful than just calling this command straight away. And if you want to call it, you have to create the main Swift file to make it the main entrance point of your app. You call that thing, and then you go further on with your either app delegate launch or the scene delegate launch. If you want to play with that, I have this code open source. You can see if it actually works, or if you can attack something, if you can attach the debugger to that. And the important thing here, you will see it in the repo, is that it won't work in the simulator because the assembly version is ARM64. But you can wrap it into these handles to prevent it from the other platforms. And the second bit to that is the actual obfuscation. So if you want to obfuscate that, you can use obfuscators, which there are plenty out of there. And there is a great talk by Camille from mdevcamp called FeedPhase about the way to decompile apps with the hex editor and how to approach obfuscation in a different way, so it modifies the compiled executables directly. And he has these obfuscator open source, so I strongly recommend you to look into that. And that talk itself is actually very, very good. And let's move on to the unusual vectors, which will be fairly quick, just the food for thought, so we can explore how you can use it in your apps. Shortcuts. Once they were launched, community was surprised by the amount of the untrusted shortcuts because, well, shortcut is a powerful thing. You can install it by direct link to the Apple server, and you don't know what it does, especially if you're tricked into installing it. They used to have access to files protected via sandbox, so nowadays it's fixed. They used to have access to protected schemas access. It's fixed as well, but we never know what might get changed. And they prone to the denial of service attacks. So let's say it might create thousands and thousands of photos in your folder. So these shortcuts themselves might be obfuscated to hide the malicious code. And that's why you have to care about them when you see if your app offers a shortcut or if your user might install a shortcut interacting with your system. Handoff, very prone to all the Bluetooth vulnerabilities. Every year there is usually one or two heavy Bluetooth vulnerabilities. Signing with Apple, a huge problem nowadays, as you've seen this zero-day issue with the JWT tokens, where Apple will just give you a token for any email straight away. It's possible to impersonate the user. There are JavaScript-related risks on other platforms because most likely you would use the JavaScript implementation framework to do the sign-in with Apple on Android or web. HomeKit, you should look out for access to unauthorized controls. So if an attacker can access your app and trigger the HomeKit control without the user noticing that, this is fairly bad. And there are some hardware issues which might be present in the HomeKit compatible devices, especially if they have their own apps. So if your app supports them, you might want to look into these apps code as well. You might want to pen test them as well. HealthKit, again, look out for interactions because app might store something temporary, and that might be a very private health data. So even if the app was granted permission to HealthKit, the user might not want it to be stored in the documents directory, for example. ARKit, it might be using the second camera in background, mostly to kind of like align the location and the position, but that still is the attack vector. And same happens with the data which it stores or caches via the app. So if your app uses ARKit, make sure that you don't store something unneeded. There is the device management system, which allows you to turn on the lost mode, the remote wipe, the remote lock. And if the user installs any certificates, and if these certificates can be compromised, they actually can have access to these modes sometimes, and they can set up the things the user doesn't expect them to set. So you should educate the users that the certificates they install are not a good thing. And there is a screen time, obviously. So when the user sees a list of apps in screen time, the apps icons are pulled directly from the App Store. And luckily, as they say in Apple Platform Security Guide, it doesn't retain any data, it doesn't cache them, it doesn't store the requests, but you still can think out of the box. You might think that the data on the user's behavior patterns is very important too, right? So the attacker might see that the user spends certain times of the day in a certain app, judging by the screen time, which might actually highlight some behavior of the user. And same applies to Safari view controllers. Overall, the silver line of these rendering is that you should care about your users. You should inform your users on their private information. You should tell them that they have the right to be forgotten, the right to correct data, the right to access their data. And if you log something, if you analyze something, if you use analytics, the first step to remove these possible concerns or issues with the security you have is to acknowledge them, is to tell your users that you have problems with storing some security data. Maybe not directly, but at least allow them to opt out from storing some data. And you should follow the Apple best practices, because even accessibility or localization will make your users feel way more secure, because they might not mistaken some field to be the field it was not meant to be there. And once you jump to the testing of that, once you think about the flow, you'll usually define the scope of the security testing first. You'll prepare yourself. You'll do the legal stuff. Don't attack the system without written authorization. It is illegal in some countries. Obtaining an IPA as a part of the bug bounty is way, way better. You would gather the information about that. You'd analyze the environment. You'll think about the architecture. You'll think about the flows the user might have, the things it interacts with. You will map out this application. You will probably scan it automatically. You'll probably see if there is a way to exploit some bits. And in that phase, you'll try to penetrate the app by exploiting the vulnerabilities, which you identified during the mapping the application bit. And then you'll get a report. And that's pretty much it, because you'll have to write down the vulnerabilities you found, document the compromises, explain how to perform them, sometimes how to fix them. And that is fairly straightforward. So the hardest bit here, because all the tools might do the work for you, and you don't have to actually write assembly code that much anymore, is this thinking out of the box, caring about the users, and thinking what can be exploited to make users' life worse. And it's our responsibility as engineers to make it better. So if that wasn't enough, and if you are feeling like you might want to dive even deeper, the iOS security guide by Apple, the explanation on how the SSL pinning works, what are the types of the penetration testings, what are the types of the exploits, the talk I gave recently on the delving into the details of the Apple Pay, and the obviously owasp mobile security testing guide are the very recommended sources. If you want to listen to more deep dive talks, the Anastasia Voitova's talk on FrenchKit last year was about the real life implementation of note encryption in some very famous, very big note-taking app. And it's very detailed. I strongly recommend you looking at that. And there is an absolutely stellar talk by Kevin Cody from the mdevcamp last year called How to Free the Good. It gives you a very, very deep dive into working with Frida and Passionfruit I mentioned earlier. You can just watch it and go straight to pen testing the apps. And please, as OWASP says, don't stop at security testing. Write your own apps, compile your own kernels, dissect mobile malware, learn how things stick, because that is the most important thing. That's what makes you a better security engineer, and that's what makes life for your users way, way better. Thank you very much. If you have any questions, reach out to me on my Twitter, follow me on my blog where I post about the security problems, and I will post links to my talks and the slides and the links to the talks I've mentioned at the website as well. I will see you at the speaker's corner, and I can take some questions now as well. Thank you.
Thank you very much, Vadim. We have one question from Slido right now. It's from Maria. Question about anti-reversing defenses. Could some of them cause issues with passing the Apple App Store review? As far as I know, reviewers can reject apps with calls to Subsystem API, might also be not happy with assembly, I guess.
So yeah, that's a very good question. Thank you. The APIs we usually call are not the private APIs. We can call the, in that case, the deny attach call, because that is used by Apple. It's documented, so it's not private. The assembly itself might raise the brow of some of the users, but that's where we can comment that properly. We can put it into the notes if you want. Honestly, I didn't have a problem with sending this exact code to the App Store, because that code, as I mentioned, gets inlined, so the analyzer itself won't see it, and they don't use the debug attaching analyzers to test our code when we send it. But yeah, that's a valid concern, as in using the private APIs is fairly discouraged, and for the right reasons.
Thank you very much, Vadim. Thank you also for the question. If anybody has any more, now's the time, last couple seconds to submit your question. Otherwise, it needs to wait for the speaker's corner. Thank you very much for your talk, Vadim. For the audience, Vadim will be at the speaker's corner for about 15 minutes, right when he jumps to the 3D world. The speaker's corner is next to the spawn point, so you don't have to worry that you will not find it. I guess after 2 days, you are pretty sure where that is. And I would like to encourage you to also vote for, not vote, rate for Vadim's talk. The poll is on right now, and we'll have 15 minutes break. Tweet with the mdevcamp hashtag, ask questions, find your speakers in the 3D world. Don't forget, if you haven't downloaded the newest version of 3D World app, do it so you can attend the after party. And also invite your friends for the after party, and we'll see you in about 15 minutes. Thank you, Vadim, one more time.
Thank you. See you in the corner.